Assalamu alaikum. This is Shamimul Islam. My ID 22308008. Today I am talking about my presentation. The topic is weather prediction with time series data. Let's go to the main part. In the first part, introduction part. Objective. Predict future temperature value using daily weather data. Compare the performance of LSTM and a simple fully connected network. Why this study? Understand the advantage of LSTM for time series data, where past data point influence future predictions. Show how different neural network structure impact predictive performance. Next step, dataset overview. In dataset overview, you can see a table with. In this table, first column represents the date and second column represents the temperature. This is an screenshot example of my dataset. And above of this table, you can see a graph. The graph represents the daily temperature over a year, while x-axis represents date and y-axis represents the temperature. Next step, data pre-processing. In data pre-processing steps, convert the date column to determined format and see it as the index. Normalize temperature using min-max scalar. Create sequence of 30 days to form input features. The blue line represents the 30-day input sequence, and the red point is next day's temperature that the model aims to predict. Here you can see the figure. This is the blue line. It represents the 30 days temperature, and this is the red point. This red point represents the next day's temperature that model aims to predict. Next step, uses model. Here I can use two types of models: long short-term memory model and fully connected layer model. First model, long short-term memory model architecture. In LSTM model, they are built three input layers, basic input layers, LSTM layers, and output layers. Input layers, sequence of 30 days of temperature data. LSTM layer, 50 units rectified linear unit activations. Output layer, dense layer with 1 unit for temperature prediction. Diagram. This is a simple flow showing the diagram of LSTM layer. This is input layer. This is called LSTM layer, and this is called output layers. Jump to the next step. Fully connected model architecture. Fully connected model architecture also builds three layers: input layers, hidden layers, and output layers. Input layers, sequence of 30 days of temperature data. Hidden layer, dense layer with 100 units RELU activations. Dense layer with 50 units RELU activations. Output layer, dense layer with 1 unit for predictions. This is a simple model architecture, fully connected model. Input layer, this is called hidden layers, and this is output layers. Next step, training and evaluations. In training, epochs 10. Epochs means epochs represent one complete pass through the entire training dataset. 10 epochs means model will go through the dataset 10 times during training. Batch size 32. Batch 32 basically. It represents how many training samples are processed before the model's weight are updated. Batch size 32 means the model process 32 samples at a time and then update its weights. Performance metrics. Also, I can say validation skills. Validation skill 20% means that 20% of trained data is not used for training the model, but instead for evaluating its performance after each epoch. Performance metrics. Performance metrics is mean square error. In mean square error, it basically measures the performance of models. Here, this is a figure for LSTM model training and validation loss. The blue line represents the training loss and orange line represent the validation loss. This figure for fully connected model. Blue line also represent the training loss and orange line also represent the training loss. Model evaluation result. Evaluation result for LSTM model 0.0827. Fully connected model mean square error 0.4249. Observation. Emphasize that the LSTM model achieved a lower MSE, indicating superior performance in capturing temporal dependency. Here you can clearly see 0.0827 is lower value of 0.4249. So this is LSTM predicted superior performance in capturing temporal dependencies. Next part, model prediction. Display a sample comparison of actual versus predicted temperature. This graph shows, you can see the black line. This is a black line. This black line represents the actual temperature, and blue dot line. This is a blue dot line represent the LSTM architecture. This is line, and orange dot line represent the fully connected model architecture. You can Here you can clearly see the blue dot line is more closer to black line temperature. So the result is highlights the LSTM models better aligned with actual value due to its temporal model capacity. Next part, interpretation. Why LSTM? LSTM retain long-term dependency in sequential data, making them well suited for time series forecasting. The fully connected network lacks this ability, leading to higher MSC. Key insight. LSTM design enable it to outperform in scenarios with strong sequential pattern. Next step. Improvements and next steps. Suggestions. Increase epochs to allow the better convergence. Add dropout layer to prevent overfitting in both models. Experiment with different sequence length and additional model architectures. Future work. Apply the models to a larger or real world dataset. Compare with GRU models for further insight. Last topics. Conclusion. LSTM model outperform the fully connected layer for temperature prediction. Illustrates the importance of model choice in the time series forecasting task. Take away. LSTMs are robust for tasking involving sequential dependencies. Thank you.